Hi, we will discuss Routh stability criteria. The Routh Hurwitz stability criterion provides a simple algorithm to determine the stability of linear time invariant system, and also it gives the distribution of closed loop poles on S-plane. To comment on the stability of the system, one should have idea about the location of closed loop poles on S-plane. If the closed loop pole has negative real part, then the system is stable. If the closed loop pole has positive real part, then the system is unstable. If the characteristic equation of any system is very complex or it is a higher order system, then it is very difficult to calculate the poles. So there is one way to comment on the stability of the system by examining the coefficients of characteristic equation. That is a necessary but not sufficient condition for stability of a linear system is that all the coefficients of its characteristic equation be real and have the same sign, and none of the coefficients should be 0. For example, we will consider one characteristic equation s square minus 5s plus 6 equal to 0. If I solve this characteristic equation for roots, then it is s minus 3 into s minus 2 equal to 0. So the roots of this characteristic equation or the poles of the system are 2, 3. So these poles are positive. So the system is unstable. Here we calculated the poles location to comment on the stability of the system. Instead of calculating the poles just by observing this characteristic equation, observe the coefficients of this characteristic equation. Here the coefficient of s square is 1. This is s square coefficient. The coefficient of s, it is minus 5, and the coefficient of s power 0, that is constant term, this is 6. Here the coefficient of characteristic equation are having different signs. So this is plus 1, minus 5 and plus 6. So directly we can say the system is unstable instead of calculating all these closed loop poles. Okay. If you take a different example, s cube plus 2s plus 3 equal to 0. This is the characteristic equation of a system. If I calculate the poles or roots of this characteristic equation, the roots are s equal to minus 1. This is one root, and the second root is s equal to 0.5 plus 1.65 j, and the third root is s equal to 0.5 minus 1.65 j. If you observe these closed loop poles, this has positive real part, this has positive real part, so the system is unstable. So without calculating the closed loop poles, just observe the coefficient of this characteristic equation. Here there is one missing term, s square term is missing. So directly you can comment, you can conclude that this system is unstable. Okay. So if the coefficients, if all the coefficients of characteristic equation are not having the same sign, or if any one term is missing, then you can conclude that the system is unstable. Okay. You take the another example. Here the characteristic equation is, say, s cube plus s square plus 2s plus 3. So here all coefficients are positive, that means they have same sign. They have same sign. And none of the coefficient is 0. And no coefficient is 0. So, can we conclude that this system is stable? No. Here, whatever the conditions that we mentioned here, this is necessary but not sufficient condition. If I calculate the roots of these characteristic equations, the roots are s equal to minus 1.275. This is one root, and the second root is 0.14 plus 1.5j, and the third root is s equal to 0.14 minus 1.5j. So here the roots has positive real part, so the system is unstable. So whatever the condition that we discussed here, this condition, it is only necessary condition but not sufficient condition. So we will go for Routh stability criteria, which gives both necessary and sufficient condition to comment on the stability of any system. Before studying the Routh stability criteria, we will study Routh array. Okay. Consider a characteristic equation, say a3s cube plus a2s square plus a1s plus a0 equal to 0. This is the characteristic equation of a system. The Routh array is calculated like this. First row, here the highest power of s is 3. So the first row should consist of coefficients of odd powers of s, that is a3, a1. Okay. Next, second row is s power 2. 2 is even number, so the second row should consist of the coefficients of s that have even power. So here comes a2, a0. Now we have to calculate the third row. Third row is calculated, so a2 into a1 minus a3 a0 by a2. Okay, so here nothing is there, so you can add zeros. Okay, so this is the first element in s power 1 row. Okay, and the second element anyway it will be 0, so s power 0, it comes as a0. Okay, this is how we have to calculate Routh array. So if we take one example, s cube plus 2s square plus 3s plus 1 equal to 0. So first s cube row, okay, coefficients of s that have odd power, so s1. Okay, this is 1. Next 3, because 3 is the coefficient of s power 1. S power 1 is having odd power. Next second row s square. Okay, so this s square row should have the coefficients of s that have even power. So here this is 2 and this is 1. 1 is constant term 1, because constant is nothing but 1 into s power 0. S power 0, 0 is even term. Now we have to calculate s power 1. Okay, so s power 1 row, how to calculate? Here 2 into 3 minus 1 into 1 by 2. Okay, based on this a2 a1 minus a3 a0 by a2, so it comes as 2.5. Okay, now how to calculate the second element in the s power 1 row? So 2 into, here nothing is there, 0, 0. 2 into 0 minus 1 into 0 by 2, so it comes as 0 only. Next, last s power 0 row. Again, 2 power 5 into 1 minus 2 into 0, 2 power 5 into 1 minus 2 into 0 by 2 power 5. Okay, so this comes as 1. Okay, so this is how you have to calculate the Routh array.